A groove metal rotor spinning inside a sealed pipe of water can bring that water to a rolling boil in under 10 minutes. No electricity, no combustion, no fuel of any kind. Just raw mechanical rotation converted directly into heat. The physics behind this phenomenon traces to a single experiment conducted in 1798, which overthrew an entire theory of how heat works. The experiment, led by Count Rumford, an American-born physicist working for the Bavarian government, used a blunt horse-driven tool pressed against a brass cannon barrel submerged in water. Within roughly 2.5 hours, the water surrounding the cannon boiled. No fire, no fuel, just a dull metal tool grinding against another piece of metal. Rumford published his results in Philosophical Transactions of the Royal Society, and in doing so, he destroyed the prevailing caloric theory of heat. Rumford proved that mechanical work could convert to heat without limit. What this means for us is straightforward. If you spin something hard enough inside water, you can boil that water. Period. 40 years later, James Joule's paddle wheel calorimetry experiments quantified the exact conversion rate, completing the first law of thermodynamics. By 1850, the principle was settled. Heat is not a substance, it is motion. This principle would later become the basis for modern applications like hydrodynamic cavitation heating. The modern application of this principle to home heating began in 1979 when Eugene Fenech patented his fuelless furnace, U.S. patent number 4,143,639. Fenech's invention was the first to apply friction heating to a sealed rotor and water design. Throughout the 80s, Eugene Perkins followed with similar devices, but the technology's commercial face belongs to James Griggs. Griggs patented the hydraulic pump in 1993. Founded Hydrodynamics Incorporated in Rome, Georgia, and attracted engineering support from NASA's Marshall Space Flight Center, specifically for high-temperature bearing design, which was documented in NASA's spin-off of 2000. It's important to note that NASA validated the bearings but not the energy claims. Hydrodynamics Incorporated still operates today, selling the Shockwave power reactor for industrial applications, including biodiesel production, brewery hop extraction, and oilfield water heating. However, they eventually dropped the residential heating product line entirely. The reason they dropped it reveals everything about where conventional heating alternatives stand and exactly where each one falls short. If you heat your home off-grid or in a rural area, you already know that every mainstream option comes with a significant compromise. Here are the 5 most common alternatives, and the specific ways each one lets you down. Electric resistance heating is the first alternative. It runs at a coefficient of performance of 1, 0, meaning you get exactly 1 unit of heat for every unit of electricity consumed. For a 2,000 square foot cold climate home requiring roughly 70 million British thermal units, BTU, of heat per year, the cost translates to approximately $3,580 annually at the current national average rate of 17.45 cents per kilowatt hour. It depends entirely on grid power, no grid connection, no heat. For an off-grid homestead, this is not an option at all. The second alternative is the cold climate heat pump. These sophisticated machines are full of circuit boards, inverters, variable frequency drives, and electronic expansion valves, each a potential failure point. They work well above freezing, but at -3 degrees Fahrenheit, the coefficient of performance drops to roughly 1.5, barely better than resistance heating, and far below the rated 3. 0. Your heating bill climbs at the exact moment you need the most heat. Installed costs range from $12,000 to $22,000 before incentives. The third alternative is the wood or pellet stove. These require 4 to 6 cords of hardwood per cold climate winter, daily loading, ash removal, chimney cleaning, and they emit particulate matter that the Environmental Protection Agency continues to regulate more strictly. Pellet stoves, the more convenient version, require grid electricity for their augers and blowers. During a winter power outage, your off-grid pellet stove shuts down. The fourth is propane or heating oil. Delivery dependency defines the experience, and price volatility can be catastrophic. During the 2014 Minnesota propane shortage, retail prices surged from $167 to $461 per gallon in a matter of weeks. Annual costs at recent averages run roughly $2,000 to $2,280. Carbon emissions and aging infrastructure that leaks are additional issues. The fifth alternative is solar thermal. It freezes in exactly the conditions where you need heat most. The glycol heat transfer fluid degrades every 3 to 5 years and requires replacement. The circulator pump that moves heated fluid from your roof to your storage tank requires grid electricity, which means the system fails precisely when a winter storm knocks out your power. A cavitation heater addresses every one of these failure points. Here's how it works. The first mechanism is direct mechanical drive. A cavitation heater connects to a windmill or water wheel through a shaft and gearbox. No generator, no inverter, no wiring. Wind turns the blades, which turn the shaft. The shaft spins a grooved metal rotor inside a sealed housing full of water. As water flows past the textured rotor surface, local pressure drops below the vapor pressure of the fluid, nucleating microscopic bubbles in the low-pressure zones behind each groove. When those bubbles are swept into higher pressure regions downstream, they collapse with violent force. The energy released by that collapse heats the surrounding water. This is the entire energy pathway, mechanical rotation converted into thermal energy in the fluid. No electricity enters the system at any point, no grid required. The second mechanism is radical mechanical simplicity. While heat pumps have circuit boards, inverters, variable frequency drives, and electronic expansion valves between you and your heat, a cavitation heater places a grooved metal cylinder spinning in water. The conversion efficiency does not change with outdoor temperature. Whether it's negative 30 degrees Fahrenheit or plus 90 degrees, the rotor converts the same proportion of shaft work to heat. There is no coefficient of performance to collapse because the mechanism does not rely on a refrigerant cycle to extract heat from ambient air. Cold weather does not degrade it. The third mechanism is zero combustion. The heat comes from fluid dynamics, not chemical reactions. There are zero particulates, zero carbon emissions from the heating mechanism itself, no open flame, no fuel to load, no ash to clear, no chimney to maintain, and no fire risk. Your insurance carrier does not need to classify it as a combustion appliance. The fourth mechanism is non-proprietary energy sourcing. Your fuel is wind crossing your land or water flowing through your property. No delivery trucks, no commodity price volatility, no propane market, no supply chain disruptions during the next polar vortex. Once the system is built, the marginal energy cost is functionally zero. The fifth mechanism, and this is the one that surprises people, is the self-heating working fluid. The mechanism generates heat from the water itself. Unlike solar thermal, there's no separate collector that can freeze, no glycol loop that degrades, no external heat transfer medium, and if wind is blowing or water is flowing, heat is being produced regardless of whether the grid is up or down. At the microscopic level, bubble collapse temperatures reach 5,000 Kelvin, with local pressures of several thousand bar. No ambient cold snap on Earth comes close to threatening the mechanism. These are the principles that drive the cavitation heater. The question now is whether the numbers hold up under independent testing. The most rigorous independent investigation was conducted by Earth Tech International in Austin, Texas, in the laboratory of Harold Puth between 1994 and 1996. They tested a USMAR unit supplied directly by its Russian inventor Isef Potapov, who had claimed a coefficient of performance between 3 and 10, meaning 3 to 10 times more heat out than energy in. Using a calibrated GE watt meter and bath calorimetry across multiple flow rates, pressures, and bypass configurations, EarthTech measured actual efficiencies between 51 and 81%. They then ran a control test, a simple gate valve creating an equivalent pressure drop in the same water loop. It produced identical heating efficiency, with no anomalous heat at any operating point. The device heated water exactly as well as a plumbing restriction. Griggs's hydraulic pump was reported by Jed Rothell in Infinite Energy magazine in 1994 at a coefficient of performance of 1.17 to 1.68 above unity. That claim was never replicated under controlled calorimetry. Tom Dromelab investigated on video and could not reproduce it. Eugene Malov's heavy water test produced a 3 to 4% effect, which fell within the margin of measurement error, a strong negative result for anyone hoping for a nuclear or exotic physics explanation. The peer-reviewed academic literature is consistent. The peer-reviewed academic literature remains consistent in its findings. Kwon and Yoon at Pan National University, in their proceedings for the Institution of Mechanical Engineers, Part C, in 2013, measured efficiencies across various rotor geometries at 80 to 96%. No over-unity claims. Vera Rosso and colleagues in the journal Energies, 2025, treated the shockwave power reactor as a process intensification tool for biodiesel production and reported consistent thermal performance without any anomalous energy production. The manufacturer's own current position is perhaps the most telling data point in this conversation. Hydrodynamics now states that the shockwave power reactor achieves roughly 98% efficiency from a shaft perspective and approximately 90% overall. They explicitly note that conventional boilers run about 87% efficiency. However, the manufacturer also points out that gas and oil cost roughly half as much per BTU as electricity. This is the manufacturer telling you that, from a purely financial standpoint, their device is not as competitive for heating purposes as conventional methods using gas or oil. Despite this, there are 3 secondary advantages to cavitation heaters that deserve mention. The first is scale-free heating. In industrial applications, cavitation heaters heat dirty, mineral-laden, or viscous fluids without the scale buildup that fails conventional heat exchangers and immersion elements. This is the technology's one independently verified advantage over standard heating methods, and the reason Hydrodynamics still sells units for oil field water treatment and dairy processing. The second advantage is water disinfection. Bubble collapse generates hydroxyl radicals, which are short-lived but potent oxidizers. This feature provides a secondary disinfection effect for a homestead, running untreated well or surface water through a hydronic loop without the need for chemical treatment. The third advantage is the absence of any global warming potential from the heating mechanism. There are no refrigerants, no HFCs, and no fluorinated gases with regulatory half-lives. Heat pumps rely on refrigerants whose global warming potential, GWP, values remain a significant regulatory concern. A spinning rotor in water, however, has none of these issues. However, these benefits, as genuine as they are, do not change the financial reality that underpins the technology. Before anything else, you need to understand the efficiency comparison that frames the entire financial case. A wind turbine driving an electrical generator that feeds a resistance heating element achieves roughly 27 to 36% wind-to-heat efficiency. Direct drive cavitation, which eliminates the generator entirely, achieves about 26 to 34%. The savings from eliminating the electrical conversion step are real, but modest, just a few percentage points. This is not a dramatic transformation in energy efficiency. Now, let's compare these systems to their direct competitors. A cold climate heat pump, such as the Mitsubishi Hyperheat or the Daikin Aurora, installs at a median cost of approximately $15,400 before incentives. After the federal 25% credit and typical state rebates, the net cost ranges from $10,000 to $15,000. Annual operating costs range from $1,200 to $1,430. A geothermal heat pump runs around $20,000, net of the 30% uncapped federal credit. A wood stove costs between $3,000 to $8,000 installed over a 20-year total cost of ownership. Here is what you're comparing. A heat pump costs approximately $47,000. A wood stove runs roughly $36,500. A propane furnace costs approximately $49,000. A DIY wind-driven cavitation system, on the other hand, costs around $67,000 or more. And that's assuming you perform all fabrication, installation, and maintenance yourself. The incentive picture makes this even worse. Federal Inflation Reduction Act credits under Sections 25C and 25D do not apply to mechanical cavitation heaters. There is no AHR, air conditioning, heating, and refrigeration, I rating, no Energy Star qualification. No recognized small wind electric generator category covers a mechanical-only heat system. USDA RAPE grants for rural energy explicitly exclude residential applications. The technology's path to financial viability becomes murkier under these circumstances. The honest, non-financial case for cavitation heating is this. The system becomes defensible only when several conditions are true simultaneously. First, you must have no available grid with utility line extensions, quoted above $30,000 to $50,000. Second, you must have an excellent wind resource, 12 or more miles per hour annual average, or a perennial hydro source with adequate head and year-round flow. Third, you must possess full DIY mechanical capability and already have backup heating for calm periods. If all of these conditions are met, the cavitation system competes on total mechanical independence, not on cost. For every other situation, and that covers the vast majority of users, a heat pump or wood stove will win on both economics and practicality. The financial picture narrows the viable audience, and the practical barriers narrow it further. Wind tower permitting is the first obstacle. Most municipal zoning codes restrict tower heights to 35 feet. A windmill generating meaningful power for a cavitation heater needs 60 to 120 feet of tower height, requiring a conditional use variance, a public hearing with uncertain outcomes. Setback requirements of 1.1 to 3 times the total tower height push the installation footprint well beyond what many residential lots can accommodate. Noise limits of 45 to 55 decibels at your property line apply. And a cavitation heater adds acoustic output beyond the windmill itself. Water rights are the single most underestimated barrier for water-driven installations. In Western states, water law operates under prior appropriation doctrine. You need a state engineer's permit and proof of beneficial use. In California, unauthorized diversion of any stream or river is treated as trespass against the state, with fines of up to $500 per day. The Army Corps of Engineers requires Section 404 and Section 10 permits for nearly any in-stream structure, with State 401 water quality certification typically required. On top of that, the timeline from application to approval ranges from 6 to 18 months, and approval is not guaranteed. Building code classification also presents a gap with no easy solution. No UL, Underwriters Laboratories, listing exists for any hydrodynamic cavitation heater, which triggers unlisted equipment provisions under the International Mechanical Code, ASME, American Society of Mechanical Engineers. Pressure vessel stamping requirements under Section 4 or Section 8 may apply to either the heater housing or the thermal storage tank. A professional engineer's stamp on the design submission is typically required, costing between $5,000 to $25,000. Many licensed engineers refuse to work on this technology outright because its online presence is dominated by pseudoscience and over-unity claims. Insurance compounds the problem. Carriers routinely exclude unlisted owner-installed heating equipment from standard homeowner policies. Any underwriter who researches the technology online encounters websites promoting physically impossible efficiency claims and treats the entire category as a fraud indicator. If you've reached this point and the technology still makes sense for your specific property, here's what the implementation path requires. Start with site assessment. For a wind-driven system, install an anemometer at the planned hub height, not ground level, for a minimum of 6 months, ideally covering your entire heating season. The threshold for viability is a site average of 12 or more miles per hour. Below that, annual heat production will not justify the capital investment. For a water-driven system, measure both head, the vertical drop available, and flow rate across all seasons, especially late summer when flow is typically lowest. You need a minimum of 10 to 20 feet of head with 25 to 50 or more gallons per minute year-round. The power mismatch is the engineering challenge most people underestimate. A cavitation heater rotor needs 1,800 to 3,600 revolutions per minute and roughly 15 horsepower per 40,000 BTU per hour of heat output. A 12-foot air motor windmill delivers enormous torque, but only about 1 horsepower peak, turning at 30 to 60 revolutions per minute. That means multi-stage step-up gearing and realistically 4 to 6 windmills worth of rotor area to meet the peak heating demand of a typical cold climate home. Pelton turbines at microhydro heads operate at 1,000 to 2,000 revolutions per minute. This is a far better mechanical match for direct shaft coupling, but only available if your property has the necessary water resources. When evaluating products for a cavitation heating system, you must be cautious about anything that claims a coefficient of performance, KOP, above 1. 0. Products marketed as over-unity, free energy, or more efficient than the laws of physics allow should be avoided. An example of such pseudoscience marketing is Kunvo's cavitation heat generator. If the sales materials promise more heat energy out than mechanical energy in, walk away immediately. The critical failure mode you should prepare for is shaft seal failure, which is a common issue across every major DIY form. The rotating seal between the high-speed shaft and the pressurized water housing is where amateur builds often die. Reports across various forms universally state this as the most common and most frustrating point of failure. Budget for industrial-grade mechanical seals and plan for replacement every 3 to 7 years. Unfortunately, no integrated installer network exists for this technology at the moment. You will need to assemble expertise spanning rotating machinery, hydraulics, ASME pressure vessel design, hydraulic heating systems, and either small wind or microhydro civil engineering. No single contractor currently offers this as a bundled service. Therefore, you're left to coordinate your own resources and possibly work with multiple specialists to get everything working. The optimal pairing for a cavitation heater is radiant floor heating, which operates on supply water temperatures between 90 and 120 degrees Fahrenheit and tolerates the slow, gradual temperature swings inherent in a tank-buffered renewable heat source. Hydronic baseboard systems are a poor match because they require temperatures between 160 and 180 degrees Fahrenheit and offer a narrow, useful temperature window. A variable output wind system cannot reliably maintain these high temperatures, making it an ill-suited choice for baseboard systems. Domestic hot water production through an indirect tank works adequately as a secondary function for the system. A properly sized insulated thermal storage tank is essential. For a design load of 30,000 to 40,000 BTU per hour, with a 24-hour buffer against calm periods, you need a tank holding 1,000 to 2,000 gallons with an R value of 25 or better foam insulation. Without that buffer, a 3-day windless cold snap would leave you without heat and with no recourse beyond your backup system. Maintenance is straightforward, but ongoing. Bearings will require replacement every 5 to 10 years. Mechanical seals need to be replaced every 3 to 7 years. The rotor itself requires an annual visual inspection for cavitation pitting, the same erosion that destroys ship propellers and dam spillways. Unhardened steel rotors last 2 to 4 years under sustained operation. Hard-coated rotors with Stellite 6 overlay or tungsten carbide applied by high-velocity oxygen fuel spray extend the lifespan to 10 to 20 years. But these come with significantly higher fabrication costs. The wind turbine or water wheel you use for the system also carries its own maintenance burden. Blade inspection, gearbox oil changes, intake debris clearing, and seasonal winterization must all be performed regularly to ensure consistent operation. Even in the narrow niche where this system is defensible, remote off-grid locations, excellent wind or water resources, full DIY capability, and a tolerance for maintaining what you build, it still faces significant competition. Photovoltaic solar paired with a cold climate heat pump typically delivers more heat per dollar spent, with vastly better code, compliance, insurance acceptance, and long-term reliability. Hydrodynamic cavitation technology represents a real physics-based solution to heating. For the small number of homesteaders in very specific situations, those with truly off-grid properties, strong wind or perennial water sources, and the mechanical skills to manage it, it offers a level of pure mechanical self-sufficiency that no other heating technology can match. But for the vast majority of people, especially those with access to grid power or standard heating alternatives, the financial and practical barriers are too great to make this system a realistic option. For most people, the better options remain heat pumps or wood stoves, which have already solved the heating challenge for the majority. This technology, while fascinating and powerful, remains better suited to niche applications than widespread use. In conclusion, hydrodynamic cavitation heating offers some unique advantages, especially in very specific circumstances. However, its complexity, high initial cost, regulatory hurdles, and practical limitations mean it will likely remain on the fringes of heating technology. While its potential for mechanical self-sufficiency and its ability to operate off-grid are compelling, it's not a one-size-fits-all solution. If your property does not meet the strict requirements of wind or water availability, mechanical ability, and a tolerance for maintenance, you may be better served by more conventional systems. The financial reality and the practical barriers will continue to limit this technology to a very specific audience. If you are one of those people, then the cavitation heater might just be the perfect fit. However, for most others, the economics and practicality of heat pumps or wood stoves will continue to prevail. And that concludes the breakdown of hydrodynamic cavitation heating technology, its potential, its drawbacks, and the reality of implementing it in today's world.